a great pleasure to have Rob here and visit us again. Hopefully, one of the many more visits.
Sure, yeah.
Yeah, I think Rob really did no introduction here. Just to sort of briefly say, Robert Nowak is a Grace Wapper professor in data science, and Keith and Jane Nosbush professor in electrical and computer engineering, and University of Wisconsin-Madison. And really, I've known Rob's work since I was a graduate student. I think pretty much anything in machine learning related topic, you name it, Rob has probably done it. Active learning, various kinds of semi-supervised and supervised learning, and all sorts of amazing work. It's really a great pleasure to have Rob here. Please go ahead.
Okay, thank you, Misha. I have to say, I've probably learned more from you than you've learned from me, to be honest. But anyway, it's great to be here. I know that a lot of people are out because of ICML and other things, so maybe some people are even tuning in. I'm going to talk about some work trying to understand how neural networks do what they do so amazingly. This is kind of an ongoing project that started really with a former student, Rahul Pari, who's joining UCSD in the ECE department this fall. I think he's not here this week. He might be at a meeting, a SIAM meeting, but he's probably settling in, so you'll all probably meet him. Also, a little bit of what I'll talk about is part of a collaboration with Ron Bohr and Jonathan Siegel, who are at Texas A&M. They're both approximation theorists, and they've kind of been helpful in kind of thinking about what we've been doing through their lens of approximation theory. But mostly what I'll talk about is joint work with two really brilliant students, Joe Shanuda and Julia Nakla, who are both at UW-Madison with me right now. The first part of the talk is going to kind of set the stage for that work. It will kind of review, hopefully some of you already know kind of the framework that Rahul and I developed. I'll kind of go over that, and then that will set the stage for some of the new things I'll be discussing. And, of course, feel free to ask questions anytime. And I don't know how the audience on Zoom, if they want to ask questions, but I'll just, yeah, there must be a way. Okay, let's see if I can go forward. Uh-oh, now I'm stalled. Why would that happen? Or maybe sometimes you have to do that. Okay, there we go. Okay, so here are some modern neural network architectures, ConvNets and transformers. Everybody knows about them. One of the common ingredients in these architectures are rectified linear units as your neurons. Also, maybe explicit weight decay used in training, or we just initialize these things with small weights, which kind of has a bias similar to what weight decay would induce. And so really kind of the starting point for our work was to think about that rectified linear unit. And I'm just going to begin by looking at shallow ReLU neural networks. And so the terminology and notation I'll use here, we have inputs. Our input weights to the neurons are W's, the output weights are V's, so W's and V's will be my standard notation, and then the output is a function of this form, where you have your input weights times the input. This just denotes the rectified linear unit. This plus symbol just says take the positive part, and V's are the output weights. I'm not going to be really careful about the bias term in the neurons. You could absorb those into the weights. Sometimes it's a little nicer from some of the analysis to do it that way. Sometimes it's nice to keep the bias term as an explicit kind of extra constant inside the neuron. If we want to discuss all that, we can do it, but just kind of maybe don't worry too much about whether the biases are absorbed into this input weight vector and we augment with a 1 or whatever. Just kind of a convenient compact notation. One of the things I want to emphasize in this talk, though, is to focus on multi-output or multitask architectures. The reason I started doing this is because I thought, well, if I'm going to look at multilayer neural networks and I understand one layer, I better understand one layer with multiple outputs. But as we sort of dove into it, we found some very interesting and curious kind of effects that are induced by multitask training. So I'm going to focus on that a lot in the talk. So this is kind of one of the main technical little observations that really kind of brings us to kind of our approach to understanding these. So if I have a ReLU neuron right there, you have an input, you have your input weights, you have your output weights. Notice the output weights, there are multiple of them because this is a multi-output kind of system. So if we train with weight decay, all we're doing is gradient descent to reduce training error rather, and then we reduce the weights a little bit each time by subtracting a tiny bit, and we just repeat. And I think everybody knows that would be equivalent to adding kind of a sum of squares weights regularization term to the training loss or training error when you're training. If you do this, what happens is that at a global minimizer of that overall training objective, then you'll get this balancing condition happening. The norm of the input weights will be equal to the norm of the output weights. I'll explain why that happens as a simple little observation in the next slide. But one thing I just want to point out here is I'm thinking about this explicit kind of weight decay regularization, but there is a lot of evidence, empirical and some theoretical evidence to say that, like, yeah, if we just start off a neural network with very tiny weights and train with weight decay, there is a kind of inductive bias or towards this type of regularization as well. Okay, so we call that neural balance, and here's just why it's happening. The rectified linear unit is piecewise linear. So what that means is I can scale the input weights by some positive value alpha, scale the output weights by 1 over alpha, and I don't change the input-output characteristic of that neuron at all. So I can kind of scale input and output weights up and down inversely to each other, and it doesn't change that input-output functionality. And then if you said, okay, so the loss term won't care at all about that scaling factor alpha, but this sum of squared weights regularization term will. And if you just simple calculation say, well, what value of alpha would make this the smallest possible, you get that square root of the norm of V over the norm of W, and that's what leads to that condition that at a global minimum, we must have these two norms equal to each other for each neuron. And so that means that this sort of usual sort of ridge regularization term, sum of squared weights, is at a global minimizer equal to the product of the norm of V times the norm of W. Okay. So what does that mean? Yeah, go ahead. Yeah. It just has to do with the homogeneity of the ReLU and the fact that here, you're sort of saying, well, if I take alpha larger than 1, I'm kind of making this bigger, but this smaller, and vice versa. So what value, you really want to have these two terms balanced. It doesn't make sense to have the input weights really big and the output weights really small, or vice versa. They just want to have those two terms balanced. And the data fitting term won't care at all, right? Because of that homogeneity of the ReLU. So again, if I go back to like this, here's the overall function. What I'm saying is if I make W bigger, I can just make V smaller and I don't change that function at all. So the data fitting term would have this in it, but then you'd have the sum of squared W's plus the sum of squared V's. And the best thing to do there is just equalize them. Does that make sense?
It's a symmetry argument.
You could call it a symmetry argument, I guess. Yeah. So let me just put that up again. So what I'm saying is the loss or data fitting term is invariant to that choice of alpha, but the regularization term is not invariant to the choice of alpha. It likes to have alpha chosen so that input-output weights balance each other. And this is an observation that was made, over 20 years ago, and then kind of rediscovered in some work by Nadi and his collaborators. So what does that mean? It kind of means that weight decay is almost like a kind of sparse regularization. And let me explain why. So here's sort of, I'm just writing it down here with squared error loss, but it doesn't really matter. We can be using any other loss function we want. So here's your data fitting term, sum of squared errors. And here's the weight decay regularization term. And as I just showed, At a global minimizer, this term will be equal to this. So we can instead optimize this objective. It's a different objective, it's a different error surface, but it shares global minimum. So the global minimum of this guy or the global minimum of this optimization. So they're different optimization objectives, but they have the same minimizers. That kind of sum of the products of the input and output weight norms is sometimes called the path norm of a neuron. And the way I really like to write it is like this. You can choose to have the input weights just normalized to unit norm. And then that term just becomes the sum of the two norms of the output weights. And this also is going to give you equivalent sets of minimizers. Of course, if I found a minimizer of this guy, the weights might not be balanced, but I just have to rescale them so they're balanced, and then you have a minimizer for this guy. So I can solve any one of these three optimizations, and I'll get the same set of global minimizers. And this just looks like what we call multitask lasso, regularization term. And if I just had one task, so y was scalar, then each of the output weights would be scalar. This would just be the L1 norm, just regular lasso. So does that make sense to everybody? Because this is kind of maybe one of the most important observations, just to kind of understand where we're going. Okay, good. So now we can start thinking about, well, what kind of functions are these guys? So again, the output of the neural network is a function f that has that form. We can take the input weights to be unit norm. So that's what this notation means. It just means they're on the unit sphere. And the output weights are just real value vectors. And then our norm of that function, we can take it to be that multitask lasso norm of the output weight vectors. So I'll call that the norm. It turns out this is a natural norm for neural functions of this form. And we could also imagine now sort of saying, well, what happens if we have infinite width or continuum width neurons? We can write, instead of a sum over a finite number of neurons or even a countable number of neurons, we can kind of take it to this continuum limit where we have an integral against a finite vector valued measure. Okay, so that's sort of, I'll explain in a minute, but basically the idea is that the norm of these functions would be the total variation norm of this measure. And that just reduces back to this case if that measure was sort of a set of Dirac impulses at a few specific VJs. Okay, so that's the finite width network is sort of just a special case of this general continuum width form. And essentially you can think of this neural variation space as a set of all functions mapping RD to RT, where T is the number of outputs, that have a finite norm, where again, the norm is the total variation of that measure. Okay, so this is a sort of function space that kind of naturally arises when you look at these shallow neural networks. So let me kind of give you a little more intuition about what these function spaces actually are. So first of all, if we look at a sort of univariate neural network. So again, there's just one input here. So this is the input X. It's just a scalar. And here's the function that a neural network would build. If I have a ReLU neural network, I'll always have a piecewise linear function. That's what I'm showing you there. Now, if I take the derivative of that function, I'll get a piecewise constant function. And if I take the derivative of that, I'll just get a bunch of Dirac impulses. And those Dirac impulses are the heights of those guys are exactly the output weights, and the locations are the biases of each neuron. So by taking the function that a neural network generates and then taking second derivatives of it, I can just basically read off what was that neural network. And we can do something similar in the multivariate case. It's a little more complicated. This was a really kind of great insight by Greg Anji and some of his collaborators a few years ago. They said, well, how can we convert this multivariate kind of problem to the univariate case? Well, what they did is they just basically took projections of the multivariate function in every direction. And if I took a ReLU neuron, so this is what a ReLU would look like in 2 dimensions. It's sort of 0 here, and then it ramps up. If you project kind of in any direction that's not sort of right along the kind of decision boundary of that neuron, you'll just get nothing out of the projection. But if you project exactly along the direction of that decision boundary, which is right here, the profile will again be a ReLU. And then we can apply exactly what we are doing up here, because essentially each one of these changes is just representing one ReLU neuron. So that's sort of the idea of how you go from univariate to multivariate. You do it through the Radon transform, or taking projections in all different directions in that multivariate space, and then applying the one-dimensional univariate analysis in each direction. So again, we can think about it this way. If we wanted to synthesize a function, we would choose a measure, which would be equivalent to choosing the input weights, biases, and output weights of the neural network. And then we can build a function that way. And then if we want to analyze the function or figure out, given the function, what was the underlying measure, we perform these operations. We take the Radon transform in each direction. We apply the second derivative operator to that projection. And then we can read off the weights and so forth of the neural network. So this norm that we were talking about, which again is the total variation of the measure, here's what the measure is. It would be take your function, Radon transform, second derivatives, that gives you a measure. And that is what's called second order total variation in the Radon transform domain. If we were in the univariate case, there would be only one direction in that situation, and then it would just be normal second order total variation. So basically, these norms are total variation norms measuring the total variation of these functions. Maybe just to go back, what's the total variation of a function like this? Well, it's how many jumps do I take in this function, which is exactly the sum of the magnitudes of those impulses. So that's what second order total variation is. And so we have a notion of that in the 1D case and also in the multidimensional case. So we can kind of go back and forth. We can build neural network functions. We all know how to do that. But then how do you, given a function, can you figure out what neural network would be the one that would represent it or approximate it well? You can do that through this Radon transform and differentiation process. And, kind of like to just give you some intuition, what this is meaning is that this norm of the function is measuring essentially something like sparsity. It's an L1 type of norm of the second derivatives in every projection direction. So what kinds of functions would have small norms? They would be functions that are very, very smooth in all projections. So you have a multidimensional function, you take all of its projections. If all those projections look super smooth, it's got a very small norm. If most of them look very smooth, but a few of them might look a little wiggly, that's also got a small norm. So these are the kinds of functions that it likes. It likes functions that are very smooth in all projections, except maybe just a small number. Because it's L1, it would maybe want a sparse number of directions where the function's second derivatives aren't necessarily so small. Okay, so just kind of a quick note on function approximation using neural networks. We can say, okay, well, now we have this function space, Radon TV2. We can take a function from that space, any function from it, and then we can say, well, how well can we approximate it with a finite width neural network? And this kind of goes back to like classical results of Andrew Barron and so forth, that we have this very nice M-term approximation. There's a neural network with M neurons that has a squared error in L2 that goes down like 1/m. And what's kind of remarkable about that is that if we took any other classical approximation method, like Fourier series, wavelets, kernels, etc., these would all suffer from the curse of dimensionality, and the approximation error would be more like m to the -1/d. So if d is very large, this is basically very, very slowly approximating the function. So we have no curse of dimensionality here, whereas we see the curse of dimensionality right there. Now, one of the questions that Rahul and I looked at with Ron and Jonathan is, are functions with finite Radon TV2 the only ones that neural networks are good at approximating? Because again, our TV2 is sort of a function space generated by thinking about neural networks. So of course, you would think neural networks would be really good for those types of functions. But are there other functions that neural networks are also good for? This is the kind of question that approximation theorists think about a lot. And it turns out we've found that No, there are actually many, many other functions that neural networks are also really good at approximating, again, getting this rate of 1/m. And there are something we call weighted variation spaces. So we kind of have a paper explaining that more generalized kind of space that neural networks are also very good at approximating functions from. Yeah.
So the cursive dimensionality here comes from the fact that this, kernels and so on, they somehow
Are isotropy,
invariant. Is
Yeah.
it a problem that
Yeah.
if you don't have some sort of directionality, you just
Exactly,
very hard
yeah.
to approximate the thing. Yeah.
What a ridge function, which with large second derivatives, so a ridge function would be a function that only has variation in one direction, and it's completely constant in all other directions. That's something that could have a small RTB2 norm, but it would have a very large norm, say in a Sobolev space or something, because you'd have to accommodate that strong variation that's only happening in this direction. You'd have to sort of say, well, the only RKHS ball I can put it in is one that allows for functions with strong variation in all directions.
So somehow, isn't that an accurate way to think about it? If you have usual RKHS space, when you have this in one direction, it kind of forces you to smooth this and force you to have variation in all directions, and that's why you're paying this one over D thing.
Yep. Yeah. Let me see. Another way to say it is that again, if I knew what this, say again, let's take a function that has a lot of weight, is wiggly, but just in one direction. If I knew what that one direction is, of course, I could design an RKHS that allows for wiggliness in that direction and assumes no wiggliness in the other directions. But the whole idea here is you don't know ahead of time which directions are going to have those strong variations. So if you take one of those functions, or all those functions, say it could be wiggly in this direction or in that direction or in the other direction. If you take all of those functions, you say, well, what RKHS ball or Sobolev ball could I fit them in? It would be a huge ball, because you'd have to accommodate potential variation in all possible directions in order, because it can't be direction selective the way these spaces can. These are Banach spaces, they're not Hilbert spaces, so they have different properties. They're more like L1 types of things. So they can have essentially sparsity in directional variation. Is there a question over there? This guy had his hand up now. I'll come over here. Yeah.
I guess the rate is dependent on the norm of the variation.
Yeah. So the constant out here would be the norm of this function. Yeah.
Maybe you answered that with this sparsity comment, but I'm struggling with this result. How useful this is. One of the challenges I've had, this is really saying that in an asymptotic sense, you have a bound on the error. And when we talk about approximations of functions, often in real life, transients matter. And this is a struggle I have with Fourier, for example. And the transients will be dropped. And maybe with wavelets also a bit better. Is there any stronger result that can be said beyond how fast or slow you diverge, which is basically the result you have?
Yeah. So that's a good question. So maybe I'll just say this, like these total variation spaces, if I just looked at, they do include certain Bezoff spaces, at least in the univariate case, which do allow for things that might have sharp transients. So they are inhomogeneous spaces in the sense that if I were looking in 1D, I could have here's a function that would have a small norm, small TB2. It'd be a function that's very smooth. Here's another function. It's a function that's very smooth, except it has a big jump right there. That also has a small norm. So it's kind of like wavelet type spaces. So it has some of those same properties to allow for spatial adaptivity to different levels of smoothness in sort of, in the univariate case, just along X, but also different degrees of smoothness in direction as well when you're in multivariate spaces. So it has interesting properties that allow you to handle things like sharp changes in behavior and transients. And I think that's what you're asking
Yeah,
about.
I think you got it. Basically, I think it's possible. So in sensor data, time series sensor data, sparsity is common. And so is heterogeneity and so on. And we cannot ignore them. We cannot smooth it with some iron or asymptotic behavior. So we look for results in which you could restrict the class. Maybe small norm is one way. Maybe there is some better characterization from continuity to computability. If it is computable, then maybe you can do something. That gives you a bit better guarantee as to what kind of functions can be approximated.
Yeah, I mean, I think you're hitting on a great point, and we have a very clear kind of complete understanding of what these functions are in the univariate case. In the multivariate case, we have some idea, like it's about this directional sparsity and so forth. Once we go to deep neural networks, we have even less understanding. I'll say a little bit about that as we go and how we're trying to investigate that. Was there another question, or maybe I just keep, yeah. Yeah, go ahead.
I mean, did you show that, okay, I mean, for functions where RTV is very infinite, there are neural networks that can still approximate.
That's right. Yep, that's what this means. There are functions that don't have a finite RTV2 variation norm, but they have a different finite norm, which is a version of that norm that's weighted in a particular way, so that that function the norm would blow up, but the weighting actually is tapering it in a certain way, and those functions are. So it's a bigger class. You can imagine I have all these functions RTV2. There's a slightly larger class of functions that still are well approximated by neural networks.
Like this compared to say other LP.
To what norm?
Any other LP.
Yeah, we can say something about that. Maybe I can, if you want to chat about it afterwards, but we can say something about, for example, what Sobolev spaces are contained in there. Basically, functions. Yeah, well, maybe let's talk about it afterwards, but yeah, but I think it might be too much to get into here. I'm happy to chat after. Okay, let me just say something quickly. We're almost done with the intro part. Something about deep neural networks. So deep neural networks essentially are just compositions of shallow neural networks. And so we could sort of say, oh, Matt, let's take function F1 through FL. These are all functions from that RTV2 function space that I was just talking about. Let's take a composition of those, and now we have a function F. So that is, what you would think about would be a deep neural network. And in fact, that's kind of what this multi-layer representative theorem tells us. It says for any data set and any loss function, there exists a solution to this variational problem. Now we're saying choose some functions to try to fit your data, but just try to find functions that have a small variation norm for each term, each function in that composition. We'd like it to have a small variation norm. So that's a optimization over these infinite dimensional function spaces. And it turns out that there is a solution that's just a multi-layer ReLU neural network. Sparse means that not too wide. The widths of each layer don't need to be larger than the square of the number of data points. And so this is kind of like telling us that, oh, okay, multi-layer neural networks, as you might expect, are really good for representing functions that are compositions of functions from the Radon TV2 spaces. So that's that thing. And it's basically telling us that, yeah, we can solve these infinite dimensional non-parametric data fitting problems by just training multi-layer neural networks with weight decay.
But there is nothing about uniqueness.
Nothing about uniqueness, because this is basically a Banach space representative theorem, and generally you won't have uniqueness like you have in Hilbert spaces when you're in these Banach.
This is not a convex problem.
It's not convex either, no. Yeah. So we can't necessarily say we can, find it, just like we can't claim to find the global minimum of training a multi-layer neural network, right? With gradient descent, we may not find a global minimizer. Here, I'm assuming we're going to find a global minimizer. This is characterizing global minimizers. Okay.
If it's all-
Yeah, it helps a lot. It's not that difficult, right? I think, but you know, it's hard to say. Yeah, maybe it's PL, yeah. Okay, so now let me give you a few applications of all this. And the first one is network compression. So again, here's the idea. Here's a shallow vector value or multitask neural network. Basically, what this means is I just have a bunch of output functions, F1 through FD out. That D out's the number of outputs I have. And we have these equivalent optimizations. We've kind of already been through this. So here's the idea. So now imagine that I just pull out a layer in a deep neural network, a ReLU layer. So these orange circles denote rectified linear unit neurons. There's some training patterns that come into that layer. They're weighted by some weights W at that layer. And then we have outputs from each neuron. I'll denote those by these phe's. And then I'll weight the outputs of those, and that's what's going into the next layer, and I'll call that psi. Okay, so I have these two matrices, phi, which is a vector of all the outputs of the neurons for each input training pattern. So there are n patterns that come out here, one for each of the input patterns coming into that layer, and then n representations coming out after we weight them. That's exactly what's going on into the neurons at the next layer. And here's a kind of layer width theorem, as we call it. You have these matrices phi and psi, let's say that you have a neural network that minimizes the overall training objective with weight decay. Then there's another minimizer with a layer width satisfying these bounds. So that the layer width is K, it's going to be less than the product of these ranks, which is always less than n times the output dimension of that layer. So n is the number of input patterns, d is sort of the width of that layer, and we can always find a possibly sparser solution by solving this multitask lasso problem. So this can be a big improvement, especially because a lot of times the ranks of these kind of representations in trained networks tend to be pretty low rank. Okay, so the idea is that you kind of start off with your trained network, you freeze the input weights, and then you just look at the output weights, and you can then solve a multitask lasso for a new set of output weights that still satisfies the same condition. So this is what's coming out of the neurons. That's weighted by output weights. We have these then inputs to the next layer of neurons. We want to make sure we don't change that overall input-output characteristic of that layer, but we can try to find a set of weights that has a smaller sum of two norms that would be like an even smaller weight decay objective or equally small. And when you solve these kinds of lasso problems, you get sparse solutions. Sparsity is sort of naturally induced by this. And so I'll say, you know, this is just a reduction to classic multitask lasso. And using kind of a generalization of Carthiodori's theorem that we came up with, you can prove this rank bound that I told you about a minute ago. And here's like something kind of curious about it. So I don't know if there are any lasso experts in the audience, but generally with lasso, if I have n inputs, I get an n sparse solution. Here, the solution will be somewhere between n and n times d, d being the output dimension. And these are just some small experiments. So the range here is 3 to 7. And you can see that we're not saturating this upper bound, which would be 7 in this case, but depending on the realization, they all have the same ranks, but we're getting different. We're solving this convex optimization exactly, and we see that in different cases we get different kind of ranks and different numbers of neurons needed in those widths. So somehow the widths of the network layers depend on something beyond just ranks. The ranks give you some bounds, but there's something else going on that we don't quite understand, some higher order structure beyond just rank. So that's kind of interesting. And let me just give you an application of this. So here we are looking at VGG19, trained to minimize cross entropy on CFAR 10. The final output layer has 512 neurons, and there are D outputs, one for each of the, or 10 outputs, one for each of the 10 classes. And so if you then apply our theory, it says, well, you really shouldn't need 512 neurons here. You should need at most 100, because the matrix ranks will be 10. And when we ran that multitask lasso procedure to find a narrower and equivalent layer representation, we found one which is 47 neurons, and it's basically in the same test accuracy and the same training loss. So you can go in, take any layer in your neural network, apply this multitask lasso procedure, and find a much narrower width layer that exactly represents the same functionality on the training data. Yeah, Misha.
These are actually a subset of neurons, right, in that layer. 47.
They're actually, so they're the same, yeah. That's a good point. Let's just say, so they would be the same, the input weights would be frozen, right? So we pick a subset of the neurons, but possibly using a different set of weights, output weights for those neurons. Different output weights, but yeah, so that's exactly right. Same subset of neurons, but or a subset of the neurons. The weights are linear. That's why it kind of reduces just to that convex optimization in that case. So we're freezing the input weights and then just saying, can we find another set of output weights that has the same input-output mapping for all the data in that layer, but with fewer neurons, and then we'll have to find new output weights to use that subset of neurons. So it's sort of like you're sort of saying, well, initially train, we're over-parameterized, but then maybe we want a smaller network to put on your cell phone so we can compress using this way, and we don't change the input-output relationship of the neural network, at least on all the training examples. How it's changing off the training examples is maybe an interesting question too, that we haven't looked at too much.
What if we just look at the best low rank prediction? Will it be even far? If the rank of the thing is even far, seven is an actually the rank.
So the rank of this matrix right here has to be 10, right?
Oh, it's to be 10.
It's 512 by 10. So the rank is definitely 10. And so the smallest you could get away with is 10 neurons, but 10 neurons won't do it in this case. The smallest we could find, and again, this is a convex optimization. It's not huge, but it's also not small. I don't know if we use CVX or what we used in this case, but we found a solution that preserves the input-output characteristic of that layer, and it just has 47 neurons. And we know that it's going to be somewhere between 10 and 100. So 47 sort of lands right in that range. But what I was saying in the earlier slide is we really can't predict exactly. Is it going to be 100? Is it going to be 10? Or where in between? It seems to depend on things other than just the ranks of these matrices in a kind of subtle way that we don't fully understand. Okay, so that was the first application. Let me tell you about the second one, and that is the regularization effects of multitask training. This was sort of a kind of surprise, but in hindsight, maybe not so surprising. But let me explain something that happens here. So suppose I give you those 6 data points. Okay, so this is a univariate problem. X is just one-dimensional, and I have 6 data points. The vertical axis is the Y. So this is a possible ReLU neural network solution. This minimizes the second-order total variation subject to interpolation of the data points. This is also a minimizer. So if I train a neural network, I could get either one of these solutions. Both are global minimizers of the training of interpolation subject to minimizing the sum of squared weights of your neural network, or equivalently, the second-order total variation. And then here are also, these are all solutions. All of these are solutions. There's an infinite number of functions that you could end up learning if you try to interpolate these data with a ReLU neural network. So, this is, again, something that wouldn't happen if we were in a reproducing kernel Hilbert space or a Hilbert space, right? We'd have a unique solution, but it's because these are not Hilbert spaces, they're Banach spaces. There are many solutions to the interpolation problem. And in this case, you could kind of say, like, well, which one of these functions would you like it to be? If you could pick one of these solutions, which one do you think is the nicest? You like a different, but if you had to pick one of these, I think I would say this is kind of bad because here in the middle, it goes so far away from the data points. Like, why would I want that to happen? Whereas this one is somehow staying closest to the data points. And there are people who have studied this problem and said, yeah, this does have what they call tempered overfitting. This has very bad overfitting. It could be catastrophic, but this is nice. So we would like somehow to get that solution. So again, yeah. So here's what you could get this solution, but if you just train to interpolate that data, but if I train to interpolate that data along with a bunch of other tasks, it turns out that I'll always get that nicer solution from the multitask training. So multitask somehow, even though I'm still interpolating the same data points, I just have a bunch of other interpolation problems that I'm not showing you. But adding those extra, basically, output tasks to my neural network, on this task, I'll get this solution rather than any of those others. I'll get a unique solution, in fact. So that's kind of crazy, kind of surprising. And in multiple dimensions, we also have, in addition to kind of like this peak versus flat kind of interpolation effect, there's also ambiguities can arise in which direction or orientation the interpolation function takes. So here I have 4 points that are at value 1, and then 4 points on a square that's larger at value 0. So it's like 4 points and 4 points, like that. And I can, if I train a neural network to interpolate these, I could get this function or this function. So totally different orientations, which is kind of bothersome, I would say, because wow, I would get totally different extrapolation from my data depending on which solution I happen to land on. And you might think that, like, over here, like, even though these data are down here at 0, it's sort of saying it's going to stay 1 everywhere out here. So it's also having this property that's not staying very close to the training points. Whereas if I train with multiple tasks, I'll get this kind of solution, which is symmetric and stays closer to all the data points, so maybe more desirable. Okay, so let me explain why this is happening. And let me do this, first of all, kind of with this model of things. So let's suppose we have T tasks. So T is some number greater than 1. And let's assume that the tasks are independent and identically distributed, just as a model. So the tasks are different, but they kind of are drawn from the same distribution. And so what that means is I have a bunch of inputs X, but then for each task, I have a different set of Ys. And the Ys for task 1 are drawn from some distribution. Then I draw a set of Ys from that same distribution for task 2, and so on and so forth. So this means that the tasks are random and exchangeable. And because of that, the output weight vectors will be exchangeable. And that just means that their distribution will be invariant to permutation. So that's one fact under this model. And then the other thing is that if T is much larger than 1, if there are many, many tasks, then if I train this neural network, keeping one task in or taking it out won't have much of an effect at all, or a negligible effect on all the others. And so kind of the intuition for why that is if I look at this over a loss function, again, I'm looking at squared error loss, but it could be a different loss, it doesn't really matter. I'll have a loss term for each task because the tasks are independent. These are basically independent random variables. So we're looking at a sum of random variables. So this will have some sort of concentration effect. Yeah.
Okay. So then when you change the weights of each task, does the result change?
So
here it's kind of like you're assigning uniform weights, right?
Right now there's so I've not done anything with the weights. I'm just saying that the Ys are conditionally independent given the X's, conditionally independent and identically distributed. And then what the claim is here is if you find a solution to this optimization, the output weight vectors in the solution will be exchangeable. Basically, their distribution will be invariant to permutation and reordering, which kind of makes sense. I could just permute the order of the tasks. That would certainly permute the order of the solution. And since the tasks are independent and identically distributed, they're invariant to permutation. The solution will be invariant to permutation.
Yeah, but I mean, what if we say certain tasks are more than the other?
Well, right now they're all IID. And this is just a model to kind of understand why what I was claiming is happening. We could come back to say, like, what if there was some tasks were more important or some tasks were large, But right now we're just kind of taking this as a model to understand what's going on. Okay, so what I was claiming just a minute ago is that if I leave one task out of the problem, it won't really affect the solution to all the other tasks. So in particular, if I have my neurons, I train with all the tasks, I'll get a bunch of neurons. If I just leave one of many tasks out, I'll essentially get the same set of neurons. So what I'm going to do then is I'm going to freeze the weights and biases of all other tasks, and then just try to find a solution to the task I left out by solving this optimization, where it's just optimizing over the output weights of that task. So the neurons are sort of determined by all but that one task. The output weights of those neurons are solved for by globally training. And then I'm just going to try to come in and say, well, how should I use those neurons to solve my final task that I left out of that initial training? Okay, so these are the things that are frozen that I put in those boxes. The only thing we're going to be optimizing here is over these VTs right there. And so if you kind of look at these norms as a function of this VTJ, this part is fixed from the training of all the other tasks. And I'm just going to take a Taylor series of that function. And you'll get, taking the second order Taylor series, you'll have some remainder. The remainder will be small, negligible, again, because this is just one task among many identically distributed tasks. So it kind of gets, the norm of this vector dominates the size of that one term. And then you can just check this first derivative of this g function is 0. And so you get this kind of quadratic function right here. Quadratic in VT. And what's important is that because in this model, the output weights are exchangeable, it means that with large probability, these norms that appear down here in the bottom are just a constant, lambda j, independent of which t you left out of the initial training. So they're just basically like constants. So I'm just repeating that right here. So what it means is that this optimization problem is approximately equivalent to this optimization problem. And that optimization problem is just a weighted ridge regression. So, and again, these lambda j's don't depend on the specific tasks that we're looking at or focusing on here. So basically, if I repeat this for each task individually, they're all basically determined by solving the same sort of weighted ridge regularization problem. In other words, the regularization term would be the same for every single task in this problem. So then, we can sort of say, okay, the neurons that we learn weakly depend on any single task. So let's let, again, capital phi denote the feature matrix composed of all the trained neurons evaluated the data points. That's basically fixed for all this analysis. Then for any one task, we're solving this kind of weighted ridge regression problem. And you can kind of just do a little kind of checking to see that that's equivalent to basically a kernel regression with a kernel function that's given by, here's the vector of neurons at a point x. So these are all the neuron outputs. And then that's what this phi transpose phi is here. And then lambda are just those weights. Lambda is a matrix where the diagonal entries are those lambda 1 through lambda capital J that I talked about on the last slide. So basically, we're doing the functions that we learn when we multicast train are kind of going to be a kernel functions. They're from a reproducing kernel Hilbert space rather than one of these Banach spaces. So let me just show you what that looks like. So here, if I just trained on these 2 squares example with just the one task, just a single output, these are the kind of solutions that I'll find. So strong orientations, or maybe sometime a little mix of those, but still, these are very typical solutions where you just end up in one orientation or the other. This is what happens when you train on that same task, but with 100 additional tasks, just with random labels, for example. You get this function, which is basically a nice smooth bump. looks like a kernel function, and this is the kernel approximation, virtually the same. The one that I just talked you through, that ridge regression problem. So it really seems to be that if you have a lot of diverse tasks and you're training a neural network, you get very different solutions than if you just train one neural network for each task. And the solutions you get in multitask training are related to these kernel spaces. Yeah, this one.
This lambda minus one thing.
Yeah, that kind of goes back to.
And these are all the same.
So each lambda j is going to be the norm of the. Essentially, this is the norm of the output weights associated with the jth neuron, and that norm is going to be it depends on j, but it will not depend on which task you leave out here, just because of that exchangeability assumption and the number of tasks being large.
Why does it depend on j?
Different neurons may be more or less important to all these tasks. So the norm of each output, so each ReLU neuron has input and output weight vector. And the output weight vectors for each neuron may be larger or smaller depending on the neuron. So that the only thing that it's definitely invariant to if capital T is large is little t, the one you left out won't have much of an effect on it. And that's just kind of Chernoff-Hufting bound for exchangeable processes result.
Do you know what trial that the kernel would be playing?
So yeah, that's a great question. If somehow all the neurons were sort of equally relevant, then all these lambda j's would be some constant. I don't, then basically this would just be this lambda here would be proportional to identity. So if somehow all those norms are roughly the same sizes, this would just be kind of related to like a neural tangent kernel or one of those other kind of kernels that people form from neurons. Kind of the idea here is that the neurons depend, of course, somehow on what all the task data were saying. But roughly speaking, if you have a lot of tasks, you could think about the neurons are somehow depending on the underlying distribution on tasks, but essentially independent of the specific realization of any single task. So it's somehow if you have an ensemble of tasks, the neurons are sort of adapted to that distribution of tasks, but they don't really depend specifically on any one task, if that makes sense. Okay, I've got a few more minutes. I think, let me just say something about in the univariate case, just because we understand this situation so much better, we can actually say something super, super concrete. It turns out that in this case, in the univariate one-dimensional case, that RKHS norm that I was just talking about is just a Sobolev space. It's just the L2 norm squared of the derivative. That's what it's minimizing. Basically the L2 norm of f prime, the derivative of the function. So we kind of completely understand that, and it's not an approximation at all that if we are in the univariate case, we almost always have unique solutions to multitask training problems, and they're always equivalent to kernel machines. That's kind of crazy because if I train single tasks, it's definitely not. So as long as I have two tasks, it reduces to a kernel method. And that's a paper that we submitted, I think, to NeurUp. So we're going to get a preprint up soon if people are interested. Okay, so I don't have much more time. I'm going to just tell you about one other thread of work, and I'm not going to go into any details. But basically, I wanted to try to understand a little bit better, like, okay, well, what exactly are these compositional function spaces that we're looking at when we look at deep neural networks? And one domain where you can kind of get an understanding is this place where they do use sort of just multi-layer ReLU neural networks with no extra bells and whistles, and that's in implicit neural representations and NeRF type problems. So that was just this representer theorem. Again, the kind of norm of regularization is the variation norm of each layer. And these are this is the application area. It's called implicit neural representations. It's also NERF, this neural rendering type of problem. But there are a bunch of challenges that people have wrestled with here. There's something called spectral bias. Again, I'm not going to have a lot of time to get into details, but basically people came up with a lot of tricks, changing the activation functions, doing some initial positional encoding, introducing other sorts of things to try to get all this to work. And they do work well. That's what NERF is doing. And it's been a success. What we said is it really true that you have to put all these extra bells and whistles on it? Or can you really just find ReLU neural networks that do the job? And it turns out the answer is yes. You don't need anything other than just a pure ReLU multi-layer perceptron. You just have to be a little more clever about how you optimize them. It turned out to just be an optimization problem. So I'm not going to say too much. I'm just kind of flashing through this. This is a paper that Joe is presenting this week at ICML, so that you can check that out if you're interested in it. And this is the one kind of 2-minute insight that we had, is that if you take 7 ReLU functions, I'm just showing you 7 different rectified linear units. If you take them and align them like this and add them up, you get something called a B-spline wavelet. B-spline wavelets have much nicer properties than a ReLU activation function. But it's still just a bunch of ReLUs, so all of our theory applies. And we get, if we just sort of effectively constrain our ReLU neural network by grouping 7 neurons at a time to kind of have some shared weights and biases, we can train much faster, we can get much better fits, better losses, and the condition number in training is much better, so it converges much faster. And what's interesting is there's still a kind of hyperparameter choice in our setting that affects optimization because it's a highly non-convex optimization. But this is what's really cool. So if you look at that variation norm that we were talking about, so here the variation norm is 8600, 2000, 1100, 1500. It turns out that the choice of regularization parameter, in this case it was 3, or sort of scale parameter was 3. The one that gives you the lowest variation norm also gives you the highest PSNR. So there seems to be a direct connection between these norms and performance in these implicit neural representation problems, which is super interesting because now you don't really have to do holdout validation or whatever. You can just kind of look at these norms and try to optimize those. And this kind of holds up over a bunch of different kind of applications and experiments. Here we were looking at tomography, but something pretty consistent in different scenarios. So I'll just stop there. Sorry, I had to rush through that last part, but thanks, and happy to take any further questions or talk afterwards.
Can you say for the norm for the Banach space?
Mm-hmm.
Can you say they induce any reflexive space if the dual is reflexive or non-reflexive?
Could you say, so you like to know a little bit more about what the norm is telling us?
Yeah.
Yeah, so this norm, if I just go back to this, so that norm is the sum of the norms of each layer. And the norm of each layer is basically going to be related to the sum of squared weights of each layer. So what this is really at the end of the day telling us is that, is a neural network with small weights better than a neural network with large weights? Well, I don't know. Maybe it is, maybe it isn't, but this is showing that it really does seem to be connected to better extrapolation and better performance. In the tomography case, you're basically extrapolating to new angles of projection, just like you would be doing in NERF scene rendering. And it's somehow saying that the neural networks, you can find many different neural networks that will fit the training data, interpolate, but then how they extrapolate is different. And it appears that these norms, which again are just the weight decay norms effectively, are a pretty good guide for which neural networks will be better at extrapolating. And so you'd like to try to find one that has small sum of squared weights, and that actually has better functional characteristics. Now, back to what those functional characteristics are, if I have a layer that has a small norm of this form, it's basically meaning that the functions in that layer are very smooth, with possible exceptions, but only in a small number of key directions. So again, I'm still not 100% sure about what that means of, say, view extrapolation in these NERF type problems, but we have some ongoing kind of investigations that are starting to shed some light on that. Like, what is the difference between how I could train a shallow neural network to interpolate a bunch of data and then say, how does it extrapolate between views? It turns out not very well. If you do just say 3 or 4 layer, multi-layer perceptron with ReLUs, you'll get really kind of impressive extrapolation between views. Why? What's going on? We're starting to kind of unpack that question and getting more insights into what compositions of functions from these RTV2 spaces are really behaving like, and they have some kind of interesting properties that seem to be key to these kind of extrapolation problems that you can't do with shallow networks. So basically, this is still an ongoing project. I'm trying to say why we hear about depth separation. Oh, you can do this with a deep network and you can't do it so easily with a shallow network. And they're all kind of a little bit contrived and not very super interesting always to me. Whereas this is a place where we have a very concrete thing that we're trying to do, extrapolate between views. Why does depth help you do that? What kind of function approximation are deep networks doing differently than shallow networks? And we're starting to make some progress towards that.
Try to look at the now, were you able to come up with a return the space being induced by this?
What is the space induced by this model?
And if there is a
Yeah, so it's one of the reasons it's kind of complicated is because so it's a composition of functions. Each of those functions in the composition comes from a nice Banach space that we more or less understand. But now you're talking about compositions of functions, and then you lose all the nice properties. So it's a function space, but it's not a vector space. So I can't take 2 neural network. I mean, I can't take 2 of these functions, add them together. They don't satisfy all the nice properties of a standard vector space. So there's just not. It's much more difficult to understand these compositional spaces, I would say. For some reason, it seems like mathematics, apart from some areas in dynamics, dynamical theory, have largely avoided compositions because you lose all the beautiful properties that you have in normal linear vector spaces. Was there something online, or Yusu had a question? Oh, okay. Did you have a question, Yusu? Yeah. Yeah.
But I saw the example.
No, so well, yeah, so yeah, if I go way back to the beginning, some of what I talked about could apply to other models, like, you know, even transformers and so forth. So basically, you know, in a transformer, you're going to have, well, this is maybe not the best one because they have convolutions, but a normal transformer block, right? You're going to have attention followed by just a ReLU, shallow ReLU, right? Attention followed by shallow ReLU. You're just re-embedding. And so we can understand, like, at least what is that shallow ReLU part doing? We know exactly more or less what it's doing. I think it's interesting because there we're always kind of in this multi-output or multitask kind of scenario. So what it's doing and what we think it's doing based on all the work that people have tried to do to understand the functional properties of neural networks, mainly focusing on just single output networks, very different if you have multi-output networks. So where that'll go, I don't know. So, but I think it is interesting just to think about also the role of the attention and that ReLU thing. There are a lot of stories about that. Of course, attention is a very evocative term for correlational analysis or whatever it is, similarity analysis. But it's really unclear to me whether we've homed in on the right best architecture for those type of sequence prediction problems. Probably not. And maybe by trying to understand some of this stuff, we'll end up engineering better systems someday. But yeah, it's slow progress. Might take 50 or 100 years. I don't know. We'll see. Maybe faster. Depends on how long Misha stays in the game.